Welcome everyone to this next installment of the derivative function. In the last video we talked about derivative formulas. This video will attract your attention to derivative rules. In our previous video we've introduced the ideas behind the main derivative formulas. So the derivative of a constant, the power rule, so powers of x, the derivative of exponential functions with base a or the special case of base e, derivatives for trig functions sine of x and cos of x. But what happens when we differentiate combinations of these functions? So for instance, what happens if we have a subtraction of two of the functions or an addition? What happens if we have constant multiples acting on them? What if we have, for instance, tan of x, which is a combination of sine and cos? What happens if we have compositions of functions, so functions inside others? So these are not things that are given by the basic formulas for the individual functions that we've seen. So what we do is we have rules for the operations that take place on the functions themselves. First of all, the constant multiple rule states that if x is a differentiable function, so in other words, the limit property or the limit definition of the derivative has to produce a finite number, and let k represent a constant, then the constant multiple rule states that the derivative of k times f of x is obtained by doing k times the derivative of f. In other words, the constant multiple stays unaffected by the differentiation process. We're going to prove this rule, and we're going to prove a lot of rules in this video, which doesn't mean this is something we'll give a lot of importance to, but it's for those who are interested in seeing how these rules are obtained. So I'm going to give a name to the function called k times f of x. So I'm going to call it c of x, c for constant multiple. We're going to prove that differentiating this constant multiple function will result in simply being k times f prime of x. In other words, that the k will just stay untouched by the operation of differentiation. You recognize by this point the limit definition of the derivative, which I'm going to apply to my function called c of x. So c of b minus c of x is the change in c over b minus x is the change in x. So rise over run is still a slope with a limit process making it an instantaneous rate of change. C at b, according to the way we've defined it, is simply k times f at b. C is a constant multiple of x. Constant multiple of f of x, pardon me. C of x itself is defined as k times f of x, and you may have noticed how k is a constant multiplier at the numerator of this fraction and can therefore be factored. Limit properties allow us to withdraw any constant multiple that we see in a limit. So the k can be removed, and if you focus only on the limit taking place, f of b minus f of x over b minus x, you will recognize that this is in fact the definition of the derivative for f at an arbitrary point called x. So this is k times f prime of x. So we've proven our point. We've proven that the derivative of c, so in other words the derivative of a constant multiple of f, will result in that constant multiple multiplying the derivative of f. For example, if you wish to differentiate 4x cubed, you can observe that 4 is a constant multiple acting on x cubed and simply withdraw it from the derivative. X cubed itself is a power whose derivative is 3x to the power 2. And then 4 times 3 is 12, so the constants put together give us our derivative formula, 12x squared. With habit, we'll just simply take the 3, which is the exponent of the x, multiply it in the front with the 4, and get directly 12. So practically speaking, we seldom go through so many steps, and that's fine. Second example, we have pi times sine of x. pi is simply a constant and can be withdrawn from the derivative, and the derivative of sine of x is cos of x, as seen in our previous video. The sum and the difference rules. So if f and g are differentiable functions, then the derivative of their sum or of their difference is obtained simply by applying the derivative to each term individually. In other words, we can distribute a derivative operation to a sum or a difference of functions. Okay, here's our proof. I'm going to start first of all by defining s of x, so the sum, as being the function f of x to which we're adding g of x. We're going to do this proof only for the sum. If you want to try it on your own for the difference, you can follow the same steps. We're going to prove that differentiating this function called s, which is a sum of two functions, is equal to the sum of the individual derivatives for f and g. Starting point, always our limit definition. So the derivative of function s is the difference between s at b minus s at x over b minus x, with b heading towards x, creating that tangent line rather than an average rate of change. What does s at b represent? It's the sum of f at b and g at b. On its side, s of x represents the sum of f of x with g of x. We will open up the parentheses and distribute the signs, and we can also rearrange the order of the terms so that the f's are placed together and the g's are placed together. So f of b minus f of x plus g of x minus g of b, all over b minus x. Fractions can always be split up if we want to, and in this case, we can even apply the limit to the individual terms of this sum. Once again, recognizing that these two limits are actually derivatives is quite helpful. Both of these satisfy the limit definition of the derivative, where we have a change in y over a change in x, and a limit process bringing the 2 points towards one another. So this is in fact f prime plus g prime, as we wished to prove. For example, here is a sum or a difference of 3 functions. So whether we add or subtract functions, the derivative of this sum or of this difference can be applied to the individual term. So notice how I've split the derivatives to each individual function. I've also done a little bit of algebra where 1 over x squared has been rewritten as x to the minus 2. And in the last term, I've extracted the 3 because 3 is a constant multiple. So I'm using the constant multiple rule that we proved a few moments ago. The little apostrophes, the prime symbols, are a reminder that I haven't yet differentiated. I've only split up the functions into individual derivatives. The power rule will turn x to the minus 2 into minus 2x to the minus 3. The derivative of cosine of x is minus sine of x, and the exponential function's derivative remains unchanged. And therefore, the outcome of this derivative, minus 2 over x cubed plus cos of x plus 3e to the x. And now we have a recipe that would help us find this function's derivative. So the function 1 over x squared minus cos x plus 3e to the x. We can find its slope using the result that we have just obtained. Product rule. If f and g are differentiable functions, then the derivative of the product of f with g is not, unfortunately, f prime times g prime. So the product rule is a little bit more elaborate. And it's obtained from f prime times g plus f times g prime. Okay, so the product rule splits up the derivatives into individual terms in which one of the functions is differentiated and not the other. And then another term which differentiates the second of the functions but not the first. So we go consecutively through the derivatives of one function at a time. Again, we're going to prove this rule, And I've started by defining the product by naming it P of x. So P of x represents the product of f with g. We're going to prove that differentiating P of x gives us the formula we're trying to get to. So f prime g plus f g prime. Starting point, as usual, is the limit definition. So P of b minus P of x is the change in y. B minus x is the change in x. P of b, the product function, calculated at b, is obtained from f at b times g at b. P of x, the product of f with g, calculated at x, is f of x minus times g of x. Here is where things get complicated because no terms are common. There's no possible factoring. So let's call the following step the tricky step. And I agree that this is not one step that we would have imagined doing without having seen it before. I will subtract, in the middle, a term called f of x g of b. And to uncheat, I will right away add it back. So plus f of x g of b. Okay, so overall, you would probably agree that the end result is going to be the same since we have subtracted and added the same amount. How is this helpful? Well, recognize in the first pair that now g of b is common. And in the second pair, f of x is common. So we will split up the fractions where we keep in each part, in each fraction, a common element. The first limit has a g of b that's common. The second limit has an f of x that is common. Here I've done two steps in one actually, which is to split the fraction into two fractions and then to apply the limit of a sum to individual and turn it into individual limits. So in the first fraction, in the first limit, g of b is a constant, is not a constant, but is a common factor. In the second, f of x is a common factor. So we will split these up, so factoring our g of b and our f of x. And we're going to use our properties of limits once again. In the first term, we're applying the limit to the quotient of f of b minus f of x over b minus x. And we're going to apply the limit to the g of b term. In the second limit, and that's a little bit magical, f of x does not depend on b, which is the actual limit variable. The variable is making b go towards x, but x itself is not changing. And therefore we can simply extract it from the limit. See if you can recognize what each of these limits will turn into. Well, the first one, the limit as b goes towards x, f of b minus f of x over b minus x, is actually the definition for f prime at x. In the second, limit as b goes towards x of g of b, well, if b is heading towards x, then g of b will have to turn into g of x. Remember, these functions are continuous, and therefore the limit has to match the value of the function at those points. F of x is not part of a limit, and then the last term, g of b minus g of x over b minus x, turns into g prime at x as we perform the limit. And this is exactly the relationship we intended to prove. Here's an example of the product rule, where we have x squared times sine of x plus 4e to the x. The product rule tells us to split up the derivatives, first of all on the first term, and then on the second, keeping the other expression unchanged. The power rule allows us to differentiate x squared, and as for sine x plus 4e to the x, we're using the addition rule to differentiate both terms, and 4e to the x stays unchanged because 4 is a constant multiplier, and e to the x's derivative is e to the x. Now, we won't prove the derivative rule for the quotient, but here it is. So f prime g minus f g prime over g squared.